Yeah, you know what? I'll present a couple of ideas today because a 10-minute window is pretty quick. But we'll go through a quick primer on concentration QTc modeling. I actually generated the data using PKPD sim because doing it using Stan is a bit more than I can cover in a 10-minute talk. We'll simulate some synthetic PKPD and then do the analysis using BRMS, which really is this fantastic jumping off point for further use of Stan code. Again, propose some ideas in terms of extensions of the analysis afforded by BRMS and Bayesian statistics in general. So concentration QTc modeling, C-QTc. QT interval is this measure of cardiac repolarization, and suffice it to say that longer QT intervals are bad news. There's this kind of unintended effect that some drugs can have on prolonging the QTc interval. Gold standard is the delta-delta QTc. It's the change in QT relative to the baseline compared to placebo. Usually that's not, we're not afforded that chance because of the fact that patients are on concomitant medications. Obviously I don't want to misspeak and these views are my own, but I think the current guidance basically says that we don't want the mean patient to have a delta QTc of greater than about 10 milliseconds. That'll warrant a TQT study. Okay, so data generation using PKPD sim. I just assumed a 2-compartment model. Here I'm plotting the central and peripheral compartment for 5 individuals that I've kind of sampled from a distribution. We're going to observe and based on drug effect on the central compartment here, where our PD data is assumed to follow an Emacs model. Hindsight 2020, I really should have just done a linear model for this case because of the fact that I could then recover the true values. In this case, I chose a 4-parameter Emacs, and so I can end up with an approximation. But in order to really validate the synthetic nature of the data, a linear model would have been better. Okay, so being realistic, I do this. I've been doing this a lot on the job. Is looking for signals, prolongation, delta QT intervals for sparse samples in particular. So I just assume that I have about 20 patients in each arm. I get samples pre-dose at sort of 0 hour and then 2 and 6 hours post-dose on the first and last days of dosing. But the patients across all the studies, obviously synthetic, receive the same amount of drugs. So 15 micrograms, 2 days on, 5 days off weekly is 120 micrograms cumulatively. 30 micrograms, 2 days on, 5 days off by week, and 120 and 30, 4 days on, 24 days off. It's also 120. We're just delivering it differently based on the schedule. Okay, if I'm agnostic to everything, I end up with this sort of picture of the QT interval as a function of plasma concentration. Obviously, I'm not saying that all this data is generated from the same patients. We have 3 different dosing intervals, and it looks like they all kind of overlap, which they do in this case because I haven't assigned different PD response based off the dosing schedule, right? It's purely related to the exposure that the patients see in their central compartment. Okay, so now we finally have this synthetic delta QTc interval as a function of plasma concentration. So I've taken all the QTc measurements and kind of subtracted off that initial baseline value pre-dose. And what we see is that we're kind of surpassing the safety threshold that again, I had suggested is a marker for significant QT prolongation in the mean patient. And I'd love to use Stan to analyze it, right? But the issue is that I find, approaching Stan is a little daunting, and especially communicating that to some of the other members of my department can be a little challenging. You know what I mean? I think that people are much more familiar with the base model building syntax in R and specifically LME4. And that's kind of what BRMS affords me, right? In addition to the fact that, in this case, I have sparse data. I have 3 measurements at 2 time points. So N is equal to 6 for each patient. It's honestly pretty good. But I have questions on what model I should assign. Should I necessarily say that I have a non-hierarchical linear model where I have a fixed intercept and fixed slope as a function of plasma concentration? Should I assume that each of my patients has kind of this varying slope, varying intercept relationship where each of them can have their own baseline QTc and then their own relationship with the plasma concentration and propagate that uncertainty to the hierarchical parameters? Whatever it may be, I think that I ascribe at least to this principle of building models fast, sampling fast, failing fast, right? This speaks to the iterative model building. But there's various questions, right? How do I check my sampling? should I then move to a nonlinear hierarchical model? In this case, the PD is an Emax as opposed to purely linear. How do I compare these models? Do I use posterior predictives? Am I using some sort of information criterion? And honestly, if I'm writing them all in STAN, is there one sort of cohesive framework by which to make this easier? You know what I mean? I don't necessarily want to have to write custom code for each posterior predictive that I'm sampling. And this is really where I think the strength of BRMS comes in as an initial prototyping tool. So over here, I have some of my, I don't have the laser pointer. Now I do. These are some of the nice backend changes that I like to make. Usually I like to run using command stand, and you can save your files. This is the simplest possible relationship, right? Delta QTc interval, it has some population intercept and population slope, follows the LME4 syntax. Great. There's some really nice things that are going on under the hood, though. We don't have time to talk about it, but BRMS is great, and I hugely advocate for it. This is what I would have written here in terms of stand code, but again, the point is that this is much more easy to understand in terms of communicating our results to the rest of my team. The other thing that's really nice, visualizations are instantaneous, right? I have all my parameters here. I can check the sampling, looks great. Assuming my fixed intercept, fixed slope here as related to the plasma concentration, I can check the population effect by calling conditional effects, and again, propagate that uncertainty in the population parameters rigorously. Fantastic. Here, this is where I should have used the linear model, but within the tidy ecosystem, I can check my parameter draws, and here we see that there is a pronounced positive effect. Again, depends on the amount of exposure, but just like this, I can also introduce hierarchy into my model, right? So now I still have my continuous variable, which is the plasma concentration, but I'm acknowledging that categorically my patients are on different dose schedules, and I also say this is this varying slope, varying intercept idea that my patients might have different delta QTCs as their baseline and different relationships with the plasma concentration in terms of the linear slope, right? So this is a categorical variable, and that's it. That's all I have to write. BRMS does a great job of compiling the code under the hood. It's about 6 seconds to run. Here, again, I haven't said anything about the nature of my data being different based on the different dose schedules. It's purely based on exposure. If the data warrants it, we can add in interactions here where necessarily that relationship with plasma concentration changes with dose schedule. Again, 6 seconds to run, phenomenal. In this synthetic data experiment, I actually think that we went into a little bit of identifiability issues here where I think this is over parameterized based on the sparsity of the data. This 15 microgram group is sort of estimated to be quite high, but again, it's beautiful that I can see this in a totally simulated environment where the slope of the population effect should be the same across dosing groups, but here it obviously isn't. Another thing, model comparison, right? I've described these 3 different models. I'd love to compare them on the basis of leave-one-out cross-validation, WAIC, which is just an extension of the AIC. In this case, BRMS suggests that the interacting linear hierarchical fit is the best. Again, I call it into question because I don't necessarily believe that the slope should be different based on the different dosing groups. And we have about a minute left. I'm just going to throw out some ideas. We're scratching the surface. We can do a ton more. Play with the noise associated with the PK, play with the noise associated with the PD. At what point do we struggle to recover our ground truth values? Nonlinear modeling. I can describe my Emax model using BRMS as well. It's really phenomenal. The other thing that I love is this notion of measurement error, missing predictors in the data. In Bayesian statistics, missing data points are nothing other than latent variables, right? And so here I can assign that some of my delta QTc values are missing, and here necessarily I could say that there's some error associated with my plasma concentration. Again, all done within this really nice syntax. And the final thing is just pull all the stand code out of this interacting linear hierarchical fit and do whatever I want with it then in the future. So I think it's just BRMS is this really nice jumping off point that enables future computation in STAN. Highly recommend these 2 textbooks. And I think that's time. Chapter 9 here is kind of where you want to look. If you want to ask me about anything here, please send me an email because I know we don't have a ton of time. And I thank you very much for this opportunity.